Hello, and welcome to Sleepy Science. I'm glad you're here, whether you've had a long day, a busy mind, or you simply love falling asleep to the sound of science. Tonight we drift far beyond our warm little planet into a place where the air is absent, the light is dim, and even the smallest speck can shape the fate of entire worlds. Imagine this, a single grain of dust floating alone in the dark, far from any star. It doesn't know it's special. Of course, dust doesn't think in the way we do, but if it could, perhaps it would hum softly to itself as it drifts, carrying secrets older than the earth. Somewhere in that tiny fragment is the raw material for oceans, mountains, and the breath of future creatures. If you enjoy these sleepy explorations, I'd be so grateful if you gave the video a little like and tap that subscribe button. It helps more sleepy scientists like you find their way here, and it means I can keep making more of these journeys for you now. You can almost see it now, just a shimmering speck against the black, turning lazily as it passes through the thin glow of a distant nebula. It's smaller than the width of a human hair, and yet, in that smallness, lies all the chemistry of creation. Silicates, carbon-frozen bits of water, all tightly bound like a suitcase, packed for a journey that will last millions of years. The temperature here is so low that nothing melts. It's colder than any place you could touch without your breath, freezing instantly. Still, even in this quiet, there is emotion. Starlight, faint though it is, pushes gently at the speck. A passing ripple in space-time from some long-ago stellar explosion nudges it just slightly. These are the whispers of forces that will one day bring this grain face to face with others like it. You might wonder, how does something so small ever amount to anything? The universe has an answer, though it takes a patient ear to hear it. The journey begins with drifting. In space, there is no hurry. A million years is just a quiet pause. The grain turns and tumbles, its edges chipped by micrometeoroids, its surfaces perhaps coated with a thin film of icy molecules as it passes through a cold molecular cloud. That cloud might be the nursery of stars, glowing faintly with infrared light as new suns flicker into being deep within it. This grain, if it could dream, might imagine joining something larger, becoming part of a pebble, a boulder, a planet. But for now, it's content to float. And here's a thought for you as you sink deeper into your pillow in all the universe's vastness. How many other tiny wanderers are out there right now, tumbling silently in the dark, waiting for their story to unfold? The scale is dizzying. Between stars, distances are so great that if our dust grains set off toward the nearest one, even traveling at the speed of a commercial jet, it would arrive long after our sun had died. But that's the thing about dust, it's not in a rush. Its life is a long, slow dance, with physics, chemistry, and chance. From here, we can follow it like a camera drifting beside it, seeing starlight catch its edges, seeing distant galaxies smear past like faint brushstrokes on black velvet. Somewhere ahead, gravity from a star system will tug it inward. Perhaps it will join a disk of other grains, swirling around a young star. Or perhaps it will be caught by the gravity of a wandering comet, frozen into its nucleus, until one day that comet falls toward a sun and releases the grain in a glowing tail. It's humbling to think that everything solid you've ever touched, rocks, bones, books, even your own skin, began as a story like this told in the language of drifting dust. You too are made of such wanderers, billions of years old, stitched together by time and gravity into the human you are now. So here it begins, this grain's journey, quiet, slow, and almost impossibly patient. The next chapter will take us to where it was born, in the brilliant and violent heart of an ancient star. But for now, you can rest here in the darkness, with it listening to the gentle hum of the cosmos, letting the distance and the cold wrap you in a blanket of quiet. The grain you've been drifting beside didn't simply appear out of nowhere. It has a birthplace, though it's nothing like a cozy nursery. To trace its origins, we have to go far back to the last heartbeat of an ancient star. Picture a sun much larger than our own, its light blazing fiercely across the ages. For millions of years, it burned hydrogen into helium, then helium into heavier elements. Deep in its core, pressure so immense it would crush anything we know was quietly forging the building blocks of dust, carbon atoms, oxygen, silicon, iron. These atoms are like shy guests at a party, waiting for the right moment to meet and bond into something more. But all stars, even the giants, have an ending. When this one's fuel began to run out, its balance faltered. The outward push of its light could no longer hold back the inward pull of its own gravity. In its final days, it swelled into a red supergiant, its surface rippling with storms larger than planets. The star began to shed its outer layers into space, a slow exhalation of gas and particles, some of which would cool and condense into solid grains. And then came the finale, a supernova. Imagine it not as a deafening bang, but as a silent bloom of light across the black canvas, bright enough to outshine entire galaxies for a brief cosmic moment. In that instant, temperatures soared to billions of degrees. Elements collided, fused, and scattered. If you could watch in slow motion, you'd see microscopic crystals forming inside this chaos. Tiny pieces of carbon silicates and metals, each destined to travel unimaginable distances. Our grain, still unshaped, was born here in the furnace of destruction. It's strange to think destruction and creation are the same event out here. The death of the star is the birth of countless worlds to be. That's the quiet paradox the cosmos loves. Nothing is wasted. Every atom finds a new story to join. Even as the star's remains billow outward, mixing with the gas between stars, new molecules are forming. Some of the dust might become part of another star. Some might become the surface of a rocky moon. Some might even someday be part of a living cell. As the expanding cloud cools, grains begin to solidify. Picture our grain now as a tiny, irregular crystal, no bigger than a speck of smoke. It's already holding within it the fingerprints of its birthplace, traces of isotopes that scientists on some faraway future planet might examine under a microscope, whispering about the star it once belonged to. In a way, these grains are like little cosmic passports stamped with the history of their journey. Ask yourself this: if you could hold it in your hand, right now, what would it feel like to know you were touching something older than Earth itself? Would it change the way you look at the ground beneath your feet, or the air you breathe, knowing they too are made of relics from ancient explosions? Over the next thousands of years, our grain joins others spilling out from the dying star. Together they form a glowing shell of debris lit by the fading heart of the supernova's remnants. Shock waves push them outward, mingling with the gas and dust already adrift in the galaxy. In some places, these clouds grow dense enough to form nebulae, vast, colorful curtains of material that to human eyes might look like spilled paint drifting in water. And yet, for all their beauty, these clouds are quiet, cold places. Our grain is now a traveler riding invisible currents through the Milky Way. It has no plan, no destination, just an endless willingness to be carried. Every so often it might collide gently with another speck and bounce away, or it might pass close enough to a star to be warmed for a fleeting moment before the cold swallows it again. The journey from here will be slow, measured in millions of years. But it doesn't matter. The grain has time, more time than any of us can truly imagine. And ahead, somewhere in the vastness, lies the next chapter, the slow, lonely wandering that will eventually bring it to a place where its destiny can truly begin. Our little grain drifts on, carried through the galaxy, like a passenger who never quite knows which train they're on, but is happy to watch the scenery change. There is no up or down here, no horizon to walk toward, only the endless depth of space. It passes through regions so empty that it can go years without encountering another particle. Then suddenly, it might brush the edge of a diffuse cloud where gas and dust are slightly denser, like walking from a silent street into a soft, slow snowfall. Light itself nudges the grain along. Photons, those tiny packets of energy that make up sunlight and starlight, don't seem like much, but out here they're relentless. A constant drizzle of them pushes against the grain's surface like an invisible breeze. This is the Poynting-Robertson effect, where light not only warms, but subtly slows and redirects a particle's path. Over 1 million years, such gentle pressure can change its course entirely. Imagine a feather drifting on a pond, moving not because the feather decided to, but because sunlight and ripples whispered it along. Sometimes the grain encounters the faint pull of a star's gravity, bending its path in a slow, graceful curve. Other times, it's caught by the shock wave of a nearby stellar wind streams of charged particles racing from young hot stars at hundreds of kilometers per second. Those winds are like invisible rivers in the dark, capable of carrying a grain halfway across a star-forming region. And then there are the encounters that are almost poetic, drifting through the faint tendrils of a nebula lit by newborn stars, or passing the cold shadow of a dark, molecular cloud where light barely enters. Here the grain may pick up an icy coating, thin layers of frozen water, carbon dioxide, or methane condensing on its surface, like frost on a winter window. This coating isn't just decoration, it's a chemistry set in miniature. Within it, ultraviolet light from distant stars can spark tiny reactions, building more complex molecules, some of which will one day become the precursors to life. Have you wondered yet how many other grains are on this same journey? The Milky Way is estimated to hold 1 trillion grains of dust each with its own history. Statistically, most of them will wander forever, never becoming part of anything larger. But the universe doesn't need every grain to succeed, only enough to seed new worlds where life might take root. It's a game of vast numbers and endless patience. Our grain, meanwhile, remains patient. It might spend 100 million years in this drifting phase, covering only a few light years in all that time. Every collision it has is a rare and delicate meeting, two tiny wanderers touching for the briefest moment before spinning apart again. But now and then, one of those meetings will be different. A gentle static cling or a perfectly slow collision might allow two grains to stick together. And that moment is coming for our grain, though it doesn't know it yet. As you picture it, tumbling end over end, lit briefly by the flare of a distant supernova in some other corner of the galaxy, you might find yourself wondering if you were a grain of dust. Would you rather wander forever or join something greater, knowing you'd lose your individuality? It's a strange choice, freedom or transformation, but out here there's no real decision to be made. Physics will choose for you. For now, though, the wandering continues. Our grain passes the ghostly outline of a gas cloud shaped by a long-gone star's wind. It drifts through the faint, cool glow of interstellar hydrogen, past the occasional whisper of cosmic rays zipping through the emptiness. And all the while, unseen, the slow pull of destiny begins to take hold. Somewhere ahead lies another grain tumbling through its own quiet odyssey, and the two are on paths that will cross. When they meet, everything changes. The meeting happens so quietly, you could almost miss it. Out here, there's no clink, no echo, No cinematic slow-motion crash, just two travelers finding each other in the vast dark. Our grain spins lazily, its tiny icy shell glinting faintly in starlight, when another grain, no bigger than itself, drifts into its path. They're moving slowly, centimeters per second, but in the frictionless emptiness of space that's enough to decide their fate. When they touch, something remarkable happens. They don't bounce away. Instead, they cling, held together by van der Waals, forces, those faint molecular attractions that are normally too subtle for us to notice on Earth. It's as if the universe whispered, "Stay." Two specks have become one slightly larger speck. If you were close enough, you'd see them wobble, their irregular shapes shifting until they find a comfortable way to fit together. This is the first step in the cosmic waltz. Once you've doubled in size, you have a little more surface area to offer a little more chance of catching another passing grain. Over millions of years, the dance continues, slow approach, gentle embrace, and then the patient spinning away as a new pair. Sometimes the partners separate, after a time perhaps knocked apart by a stray collision, but often they hold fast, ready to invite more into their growing cluster. And clusters they do become. 2 grains become 3, 3 become 10. 10 becomes something large enough to look like a tiny puff of smoke. This is the foundation of planet-building quiet gatherings of dust hidden in the swirling fog of a young star system or a dense molecular cloud. If you could shrink yourself down and wander through one of these clusters, it would feel like floating inside a slow-motion snowstorm where each flake is eager to join hands with another. You might be wondering, why don't they just drift apart again? The answer is a mix of physics and persistence. These early bonds are fragile, but in the microgravity of space, nothing pulls them apart unless another force intervenes. And the stickiness isn't only physical, it's chemical. Dust grains often carry electric charges from interactions with cosmic rays or ultraviolet light. Opposite charges attract, adding a subtle but meaningful pull. Think of it as a microscopic version of magnets clicking together, only with much less certainty and much more patience. Every new collision changes the shape of the growing clump. Some arrive head-on, others graze, and cling at odd angles, building a lumpy, irregular form. It's not graceful, but it's effective. And here's a quiet truth. This chaotic assembly is what eventually leads to the perfect roundness of planets. Gravity, once it grows strong enough, will smooth out every lump, but for now the irregularity is part of the charm of... There's another layer to this dance, literally. As clusters grow, they become more shielded from light and radiation. Inside chemical reactions can occur in peace, allowing icy coatings to react and form more complex organic compounds. Somewhere in these protected interiors, the first building blocks of life's chemistry may already be taking shape long before a planet even exists to host them. Imagine our grain now no longer alone, but part of a slightly larger, more confident little clump. It has met others, shared its path, and started a journey toward something far bigger than itself. Yet it can't see the future, can't know that in a billion years, this humble cluster might be part of the crust of a newborn planet, or even the soil beneath the roots of alien trees. Here's something to think about as you breathe slowly and sink deeper into rest. How many beginnings are happening right now in the quiet corners of the cosmos, invisible to us, but unstoppable. All the same, every star, every planet, every drop of water once began as a meeting like this. 2 specks brushing gently in the dark. If you could shrink yourself down small enough to perch on the surface of our growing dust clump, you'd feel the faintest tickle of an electric field brushing past you. It's almost like static electricity after shuffling across a carpet, except here in the vacuum of space, that gentle electric tug is one of the most important forces at work. These tiny charges are born from light and collisions. Ultraviolet photons from distant stars knock electrons loose from the dust's surface, leaving it with a slight positive charge. Or in colder shadowed regions, the opposite happens. Free electrons in the surrounding plasma settle onto the dust, giving it a negative charge. Our little clump might even have different charges on different parts of its surface, like a patchwork quilt of attraction. And this is the universe's invisible glue, electrostatics. When two charged grains drift close, they can feel each other from a short distance away. There's no sound, no visible spark, but the pull is there. If their charges are opposite, the attraction is stronger. Even if they're the same, the random jostling of their irregular shapes might still let them snap together, sticking like lint on wool. This is what allows the tiniest cosmic gatherings to survive. Without it, collisions at this scale might just bounce apart endlessly. Instead, a lucky charge can hold two grains in place, long enough for other forces, like the thin tendrils of molecular bonding or the grip of frozen ices, to seal the connection. Picture the cluster now tumbling gently as it drifts. Each time a free grain approaches, it feels the whisper of that electric pull. If it's moving slowly enough, the attraction wins, and the grain is absorbed into the growing whole. Over thousands of years, the surface of the clump becomes a mosaic of minerals, ices, and tiny pockets of trapped gas. Each grain that joins leaves a little of itself, behind a trace of its birthplace, a fragment of its history. Now imagine a whole region of space filled with these gatherings. This is the early stage of what scientists call coagulation, a quiet rain of dust onto dust, forming ever larger structures. It's happening right now in young star systems across the galaxy, in disks of gas and dust that spiral like glowing vinyl records around newborn suns. There, electrostatic forces are constantly at work, knitting together the smallest pieces so that gravity can eventually take over. Have you ever thought about how delicate the early steps of creation are? It's almost comical that something as small as a static, cling the same thing that makes a sock stick to your sweater, can lay the foundation for a planet. But that's the beauty of the cosmos. It builds cathedrals from cobwebs, one invisible thread at a time. Our grain, now part of a small but steadily growing cluster, may have doubled in size since the last time we checked in. That's still impossibly tiny by human standards, perhaps a fraction of a millimeter, but in cosmic terms, it's progress. The more surface area it has, the more grains it can catch. The process speeds up little by little, as if the universe is rewarding patience. And in the spaces between these gentle collisions, chemistry is quietly at work. Energy from passing light and cosmic rays stirs up reactions in the icy layers. Molecules combine into more complex forms, alcohols, hydrocarbons, even amino acids in rare cases. These aren't life, but they are life's alphabet, waiting for a planet to become their page. Somewhere in the future, gravity will pull much harder, and the collisions will grow more dramatic. But for now, it's the quiet pull of electrostatics that shapes our clump's fate. No fireworks, no rush, just a slow and steady gathering under the faintest of forces, like dust settling in the corners of an endless starlit room. From a distance, our cluster of dust and ice still looks like nothing more than a fleck in the void. But up close, it has changed. Its surface is rougher now, bristling with tiny protrusions where new grains have latched on. Each one carries a different mineral or icy compound, adding to the diversity of the little world in progress. And slowly, almost imperceptibly, it's growing beyond the stage of a mere clump. The leap from dust specks to pebble-sized bodies is all about persistence. In the microgravity of space, there's no friction to slow a grain's tumbling, no air resistance to make it settle. Instead, the growth happens through thousands upon thousands of collisions, most of them so gentle they wouldn't even ruffle a feather. Imagine an endless snowfall where every flake that lands stays stuck to the one before it until the heap becomes something you could hold in your hand. But space is not perfectly still. Turbulence stirs the gas around our cluster. The motion of the young star system's disk creates zones of slightly higher density where more grains drift together. These regions are like slow-moving conveyor belts, bringing new material within reach. With each addition, our cluster's mass increases, which means its movement changes too. It's no longer as easily pushed around by light. It has enough weight now to keep drifting on a more stable path. This is also when collisions start to matter in a new way. At very small sizes, a grain's stickiness comes from electrostatics and molecular bonding. But as clusters grow, they begin to absorb impacts better, flattening slightly, redistributing the force, holding on, instead of breaking apart. When two larger clusters meet, they might shatter a little, but much of the debris remains nearby and is quickly reabsorbed. Nothing is wasted. There's another quiet benefit to growing larger thermal inertia. Tiny grains heat and cool instantly when exposed to starlight or shadow, but a pebble-sized body can hold its temperature longer, allowing chemical reactions in its icy or dusty layers to proceed more steadily. Over thousands of years, this stability encourages more complex compounds to form things that in the right place and time might later spark biology. If you could run your fingers across its surface, now it might feel like a porous, volcanic rock full of little voids where icy gases are trapped. Inside those pockets, there's a strange sense of anticipation, as though the cluster itself is waiting for its next chapter. And that chapter is about to come because something shifts once it reaches pebble size. Gravity begins to have a voice. It's a whisper at first, so faint it only matters during the gentlest of encounters. But unlike electrostatics, gravity doesn't care about surface charge. It always attracts, always encourages union. As the pebble grows, that whisper will get louder, and soon it won't just be catching other grains by chance. It will start pulling them in. Ask yourself this: if something so small and simple can patiently grow into something that can shape its own destiny, what might patience allow in our own lives? Out here, progress is invisible day to day, but inevitable over the long arc of time. Our pebble in the making keeps tumbling in the dim light of its young star, coated in minerals, carbon compounds, and ice. The collisions are no longer rare. This is the busy part of the disk, where billions of particles are swirling, meeting, and merging. The slow waltz of grains has become a steady rhythm each step, bringing it closer to becoming something entirely new. The snowball effect is waiting just ahead, ready to take over. There comes a moment in every growing body's life when the odds tip dramatically in its favor. For our pebble-sized cluster, that moment is now. It has crossed a threshold, not just in size, but in influence. With every bit of mass it's gathered, its pull on the surrounding particles has grown. What was once the faintest gravitational whisper is becoming a steady murmur. The snowball effect is underway. Here's how it works. In the earliest stages, growth depends on luck. A grain happens to bump into another grain, and they stick. But now our pebble can reach out, subtly bending the paths of nearby dust and smaller pebbles toward itself. It doesn't reel them in like a planet does. Its pull is still gentle. But in the microgravity ballet of the disk, even the faintest attraction can mean the difference between a near miss and a capture. And once something does stick, the pebble's size increases, which makes its pull just a little stronger. That brings in more material, which makes it even stronger. It's an accelerating feedback loop, a cosmic version of the more you have. the easier it is to get more. It's not greed, it's physics. Picture it now. Our pebble spins slowly as smaller grains rain against its surface, each one adding a microscopic layer to its form. Some hit head-on and vanish into the porous interior. Others glance off but leave behind tiny bits of ice or mineral that cling to surface ridges. Occasionally, a larger fragment, another pebble, perhaps drifts into range. The collision might be messy, breaking both bodies into pieces, but in the chaotic swirl of the disk, those fragments don't escape far. Gravity corrals them back, and soon the whole mass is bigger than before. It's during this phase that growth becomes rapid on cosmic timescales. What took millions of years before can now happen in mere thousands. The pebble grows into a rock, the rock into a boulder. Imagine its shadow lengthening, though in space shadows stretch forever over the dusty plains of the disk. Around it, the environment is changing too. The disk itself is evolving. Gas is beginning to drift inward toward the star, leaving behind lanes where dust concentrates, making collisions even more likely. Have you ever rolled a snowball downhill, watching it pick up more and more snow until it's too heavy to push? This is the same process, except the hill is gravity. The snow is a mix of rock and ice, and the slope stretches across millions of kilometers. Our boulder's surface is now an intricate patchwork, dark carbon-rich crusts in some areas, glittering ice crystals in others, metallic flecks embedded like stars in stone. Inside, pressure is building, not enough to melt rock or ice yet, but enough to compact the innermost layers. Tiny voids collapse, and trapped gases are squeezed into even smaller pockets. If the boulder could think, it might feel a growing sense of cohesion, a readiness for the next stage. And here's the thing, from here on out, growth can take unpredictable leaps. A single lucky collision with a much larger body could double its size in an instant. Or it could spend hundreds of thousands of years sweeping up the smaller debris, growing slowly but steadily. Both paths are possible, and the outcome will depend on the chaotic choreography of the disk. In the stillness of your room, imagine floating alongside it now, feeling that faint tug of gravity even at a short distance. It's not enough to pull you in yet, but you can sense that it's no longer just a passenger in this cosmic current. It has become a quiet collector, a body with a purpose written into its physics: grow and keep growing until the next great transformation begins. The place where all this is happening is not just empty space, it's the bustling, swirling heart of a young star system. Picture a vast disk of gas and dust spinning around a newborn sun, stretching billions of kilometers from its bright center. This is the protoplanetary disk, a glowing workshop where worlds are forged. From your perch beside our growing boulder, you'd see the disk as a wide, hazy plain, with the newborn star blazing at its center like a lantern in fog. Closer to the star, the heat is fierce, so intense that only metals and rocky materials can survive. Further out, beyond what scientists call the frost line, ice can persist without melting, and the building blocks here are richer in frozen water, methane and ammonia. Our boulder drifts somewhere in this cooler region, surrounded by countless others, all dancing under the same physical laws. The disk is not uniform. Spirals of denser dust snake through it, carved by the gravitational influence of larger forming bodies, or perhaps even the faint tug of the newborn star's magnetic field. These spirals are like cosmic highways channels, where dust concentrates and collisions happen more frequently. In some areas, turbulence stirs the gas into eddies, trapping particles in swirling pockets. You can imagine our boulder drifting into one of these zones, like a leaf caught in a gentle whirlpool where the density of its neighbors suddenly multiplies. This is where growth accelerates again. In these denser lanes, the odds of meeting another boulder rock or icy fragment shoot up. Some encounters are slow and friendly, allowing mergers. Others are rough, smashing surfaces into clouds of smaller debris that quickly fall back together. The disk's environment ensures that even destruction leads to creation. Nothing is truly lost. Here only rearranged. The light from the young star filters through the dust in warm, muted tones, turning the entire sky a golden haze. Occasionally, bursts of radiation from the star flare outward, stripping gas from the inner disk or sending shockwaves rippling through the outer regions. These flares may shift the paths of smaller particles, some of which end up in the gravitational embrace of our boulder. If you think about it, the disk is like a vast bakery with countless ingredients moving through giant, invisible mixers. In the warmer zones, rocky dough is kneaded and shaped. In the cooler reaches, icy glaze collects and coats the forming worlds. Our boulder is part of this recipe, one of millions of lumps in the mix, each with its own story, but all headed toward the same destiny, becoming part of something bigger. From the surface of our boulder, the disk's motion feels eternal, everything slowly circling the star in the same direction, though at different speeds, depending on distance. Sometimes a far-off shadow passes the silhouette of a much larger object, already a kilometer or more, across, moving like a whale through a sea of minnows. One day, such a giant might become a planet. But for now, our boulder remains in the middle tier of creation, too small to dominate, too big to be ignored. And so it drifts in the dusty lanes, collecting specks, pebbles, and the occasional shard of ice. It doesn't know that it is in a race against time. The protoplanetary disk will not last forever. Over a few million years, the star's winds will blow away most of the gas and fine dust. Anything that hasn't grown large enough by then will be left to wander the system's outskirts or fall into the star. For our boulder, the clock has started ticking, but in the slow language of the cosmos, there's still time to grow. Our boulder's growth spurts have made it something more than just a drifting lump. It's now a planetesimal, a name that sounds like a bedtime fairy tale creature, but in truth marks a major milestone in the life of a world to be. At tens of kilometers across, it has enough gravity of its own to pull on nearby dust and pebbles. It's not just swept along by the currents anymore. It subtly bends those currents toward itself. From the surface, if you could stand here without a spacesuit, which admittedly would be a very brief experiment, you'd feel the faintest pull toward the center. It's not much, far less than Earth's embrace, but enough to make particles drift down and stay instead of bouncing away forever. In a quiet, persistent way, the boulder has become a collector, drawing in whatever wanders too close. But gravity's new gift comes with new challenges. In the protoplanetary disk, being big means being noticed, and not all who notice are friendly neighbors. Other planetesimals roam these lanes, each with its own hunger and momentum. When two of them cross paths, the meeting can end in a graceful merger, or in an explosive shattering, scattering fragments far and wide. These encounters are determined by velocity. If they're slow, the embrace wins. If fast, the collision becomes a violent spray of debris. Here's something to wonder as you watch: how many worlds never made it past this stage. How many were broken apart and recycled their pieces, becoming the seeds for entirely different planets. The truth is, space is not wasteful. Even in destruction, the dust and shards simply rejoin the great dance, ready to stick somewhere new. Our planetesimal is lucky for now. Most of its encounters are gentle grazes, like two dancers brushing fingertips in a crowded hall. A pebble here, a chunk of ice there. Its surface becomes patchwork, mottled with materials from places far away in the disk. Each addition tells a story of a journey, a fragment from the warmer inner zones, carrying metallic glints, an icy shard from the cold outskirts, carrying hidden molecules that will one day be the chemistry of oceans and atmospheres. Sometimes the approach of another body is a slow, hypnotic drift, taking days or weeks before they meet. From the planetesimal's point of view, it's as if the other object is falling in love with it, drawn closer and closer until they finally touch and never part again. And just like that, the mass grows. In the background, the young star keeps up its subtle shaping of the neighborhood. Its light pushes on the tiniest grains, while its gravity sets the pace for every orbit. Magnetic ripples in the surrounding gas can nudge planetesimals inward or outward, shifting them into new feeding grounds. And every so often, a burst of energy from the star jolts the whole system, rearranging the lanes of traffic like a cosmic detour. Our planetesimal doesn't know it, but its growth is also a race against something invisible: orbital resonance. Larger bodies forming nearby can trap smaller ones into rhythmic paths, limiting their freedom to roam and feed. To escape that fate, it must grow enough to either break free or join the larger competitor. It's a quiet competition waged without intent, but the stakes are nothing less than planetary destiny. As the planetesimal spins lazily in its orbit, the surface tells the story of these years. Craters from small impacts pockmark it like freckles. New layers bury older ones, creating a time capsule of dust and ice. If you slice through it, which we won't, it's trying very hard to become something you'd see a jumble of materials from across the disk pressed together by its own gravity. The protoplanetary disk is still thick with opportunity, and our little collector is making the most of it. Day by day, year by year, it fattens in the haze, drawing closer to the threshold where something dramatic will happen, a moment when its own gravity will stop being gentle and start becoming fierce. There comes a moment when growth tips into transformation, and for our planetesimal, that moment is here. After countless quiet collisions, it's now hundreds of kilometers wide. Gravity no longer just coaxes pebbles and dust, it actively shapes the entire body, squeezing it into something nearly spherical. The lumpy, irregular days are over. Now, under its own pull, it's smoothing out like dough settling into a round loaf. This rounding is more than cosmetic. Deep inside, pressure begins to rise. Each new layer of material presses down on the ones beneath, heating the interior. Some of the heat comes from radioactive decay of certain isotopes locked into the rock and ice. Some comes from the sheer force of impact's energy converted into warmth. And warmth in the quiet dark is a restless thing. It melts ice locked in the pores, loosens minerals, and over time allows denser materials like iron and nickel to sink toward the center. Lighter silicates and ices float upward. The planetesimal is becoming layered. A metallic heart, a rocky coat, maybe a thin, icy shell. This process, called differentiation, is one of the great turning points in a world's life. It turns a jumble of stuff into an organized body with a structure, a personality of sorts. Pause and picture this: a molten core quietly spinning, wrapped in rock, all enclosed by an icy crust. If you could listen closely, you might hear the distant creak and groan as the materials shift into place, a slow settling that will last millions of years. Does every world get this far? No. Many stay as cold rubble heaps, never warming enough to sort themselves out. Ours has been lucky and greedy. But even as it changes within the world, is still very much part of the chaotic ballet outside. Other planetesimals roam, some now large enough to tug on it from afar. The bigger it grows, the slower it orbits in its lane, making certain meetings inevitable. When two large bodies approach each other, the stakes are enormous. They might merge into something twice as massive, or shatter each other, erasing millions of years of progress in a single day. One day, a giant from further out in the disk drifts into range. It's similar in size, perhaps even bigger, and the two begin their slow-motion spiral. Weeks pass as they circle closer, their paths warped by mutual gravity. Then impact. It's not an explosion in the way we know on Earth. Here in space, there's no air to carry sound, no roaring shockwave. But energy still transfers in unimaginable amounts. Mountains crumble, crusts melt. Molten sprays freeze instantly into strange glassy shapes. The two bodies become one, their materials mixing into something new. This collision is both violent and creative. It delivers fresh metals to the core, stirring up the layers. It adds angular momentum, changing the spin rate. And perhaps most importantly, it clears the immediate neighborhood of dangerous rivals, at least for a while. Our world now commands respect. It's a true protoplanet, a planetary embryo. The dust and gas in its lane flow differently because of its presence. It casts a gravitational shadow, sweeping clean the space around its orbit. It's beginning to shape the architecture of the solar system it will call home. There's still danger, of course. Stray planetesimals from other lanes can wander in. Gas currents can tug the protoplanet closer to the star or shove it outward. And far-off giants still forming may send gravitational waves through the disk that nudge it into new paths. But in this moment, it's thriving, layered, rounded spinning in a steady rhythm. And deep in the molten heart metals swirl. This movement may someday give rise to a magnetic field, a shield against the charged particles streaming from the young star. It doesn't know it yet, but such a shield could mean the difference between keeping an atmosphere and losing it to space. Our protoplanet has grown from invisible dust to a layered living sphere in the cosmic sense. But it's not done. Ahead lie storms of stone, oceans of molten rock, and an encounter that will change its face forever. The star in the center of this young system is still restless. It throws off flares that leap millions of kilometers, flinging charged particles like invisible rain into the disk. Out here, the protoplanet feels the constant press of this radiation, but it's also aware, if a world could be aware, that its own growing mass gives it a kind of authority. Yet the neighborhood is far from peaceful. Across the orbital lanes, other protoplanets are jostling for position. Imagine a slow-motion demolition derby, but with contestants the size of small moons or Mars and collisions spaced out over thousands of years. Every so often, a stray interloper swings into the protoplanet's path. Sometimes the visitor is small, a welcome snack. Other times it's big enough to rewrite the rules. One such encounter is on the horizon. The newcomer is massive, almost equal in size, trailing a wake of dust and debris like a comet's veil. They are drawn together, not by choice, but by the inevitable pull of gravity. This is no gentle greeting. This is the kind of meeting where worlds remake themselves. When the impact comes, it's on a scale that defies human terms. For a moment, the combined surface becomes an ocean of molten rock glowing orange against the black. Fragments as large as mountains are thrown into orbit, swirling into a glowing ring. The two bodies fuse their cores, mingling in a storm of liquid metal. From this chaos, something unexpected happens. A portion of the ejected material stays aloft. Over the next months, it clumps together, pulled by the very world it came from. This ring becomes a companion, a moon. Small compared to the protoplanet, but big enough to influence tides in the magma oceans and much later in liquid seas. Pause here and ask yourself, what would a world feel if it could feel about having a moon? Would it sense the tug every orbit? Would it feel less alone in the vast dark? In our story, the answer is yes. This is the beginning of a lifelong dance between planet and satellite. The moon's gravitational pull begins to stabilize the protoplanet's spin, giving it steadier days. Without this, the axis might wobble wildly, making climate and weather far less predictable. It's an invisible gift, a quiet presence in the sky. Meanwhile, down on the surface, the magma seas are cooling. Slowly, black crust forms over red-hot depths. Volcanoes punch through spilling fresh rivers of molten rock that glow like veins under thin skin. The air, if you could call it that, is thick with steam carbon dioxide and traces of other gases boiled out from the interior. It's a harsh place, but every drop of water vapor, every molecule of gas is the beginning of an atmosphere. Beyond the star's light grows steadier, and the disk begins to thin. The time of frequent colossal impacts is fading, replaced by more subtle shaping forces. The protoplanet's orbit settles its gravitational influence, carving a clear path through debris. It has become a true planet in all but name. And yet there's still one more stage ahead, the slow settling into a mature, fully formed world. To reach that point, it will need to endure the last great storms of its youth. Storms of rock, storms of ice, storms of fire. For now it spins on moon in tow, molten heart beating quietly beneath a dark crust, dreaming of ocean skies and perhaps someday life. The disk around the young star is thinning now, but the last scraps of its material are not idle. Out beyond the planet's orbit, swarms of icy bodies drift inward, carrying with them frozen water, carbon compounds and exotic ices that have never known warmth. They are the silent messengers from the cold reaches where sunlight is faint and time feels slower. The planet, still warm beneath its crust, welcomes these icy visitors in a rather dramatic way. Each impact is a flash of light, a shock wave, and a brief new crater in the darkened surface. In human terms, it's a little like being in a gentle rain shower if each raindrop were the size of a skyscraper and arrived at 20 kilometers per second. But to the young world, it's nourishment. Some of the larger icy bodies break apart before they even reach the surface, scattering their cargo high into the atmosphere. Steam billows upward, mingling with volcanic gases, building clouds thick enough to block the sunlight for days. When the vapor cools, it condenses and falls back, raindrops sizzling instantly as they hit the still warm crust. You might wonder, does the planet notice the gift it's being given? If a world had feelings, would it be grateful for these icy strangers? Perhaps, in its own slow language, the answer would be yes. After all, this is the start of its oceans. Meanwhile, the moon continues its patient orbit, tugging gently at the planet's crust. These tides are not of water. There are no seas yet, but of molten rock deep inside. The constant stretching and flexing stirs the planet's interior, driving currents of magma that feed volcanoes and help release more gases into the air. Over millions of years, the impacts grow less frequent. The great bombardment fades into occasional smaller visits. The planet's crust thickens its volcanic outbursts, becoming less constant, more episodic. But the atmosphere is richer now, thicker, with traces of nitrogen carbon dioxide, and in time, the first whispers of oxygen from chemical reactions on the cooling surface. The skies are still heavy and red-tinged, the sunlight dimmed by haze. But the first stable pools of liquid water begin to appear in low basins, steaming in the warmth. They are small, shallow, and sometimes vanish when fresh lava floods in, but they mark a turning point. The planet has crossed into a new phase, one where water can linger and shape the land. It is here that the seeds for something extraordinary are sown, not in a sudden moment, but in the quiet accumulation of ingredients. Dust from space rock from ancient collisions and ice from the far reaches have all played their part. The result is a place that no longer feels like a raw fragment of cosmic debris. It feels like a home in the making, And if you could stand on the still barren surface and look up, you'd see the moon hanging there, bright, serene, and loyal. A reminder that even in the chaos of the early solar system, some bonds endure. The pools of water, once just fleeting guests on the surface, begin to linger a little longer. They gather in basins carved by ancient impacts, shimmering under the filtered light that seeps through the hazy sky. The air smells of minerals and volcanic gases, sharp metallic and faintly acrid, a scent that only a very new planet could wear so proudly. The moon, tireless in its orbit, keeps stirring the young world's interior. Its gravitational pull continues to flex the crust, feeding a restless network of volcanoes. Each eruption sends plumes of ash and gases high into the atmosphere, adding layers of complexity to the air and sprinkling the ground with fresh minerals. It is as though the planet is seasoning itself, scattering the ingredients for something yet to come. You might pause here and ask yourself, if you could visit this world, now would you recognize it as the ancestor of the living planet it will become? The land is still mostly bare rock, the sky a perpetual swirl of red and gold haze, the waters tinted and warm. It would seem alien and unwelcoming to human eyes, but it is perfect for what needs to happen next. From space, you'd notice that the impacts have slowed even more. The solar system has entered a calmer period, the great construction phase nearly done. The planet's path around its star is stable, its tilt gentle enough to avoid extremes, its companion moon still holding the rhythm of its spin. This is the quiet between storms, the time when subtle, slow changes take over from the loud drama of collisions. Beneath the surface, hydrothermal vents hiss and bubble, churning mineral-rich water. These are deep, dark cauldrons where the chemistry of rock and water begins to mingle in earnest. Out on the land, rain from the thick clouds begins to carve channels into the soft crust, carrying sediment toward the low-lying pools. Every drop carries whispers of elements, forged long before the planet existed: carbon from ancient stars, sulfur from deep space dust, iron from the heart of shattered worlds. In this way, the stage is set for an entirely new chapter, one not written in craters and magma flows, but in the quiet rearrangement of molecules. The planet is no longer just a place. It is becoming a system, with air, water, and solid ground working together in a slow, intricate dance. The dust that began this journey, those tiny specks drifting between the stars, has now given rise to mountain seas and an atmosphere. The transformation is not complete, but you can already sense the direction. The world is no longer a random assembly of rock and ice. It is something that can host the possibility of life. And though there is no one to see it yet, the sight is beautiful in its own raw way. The moon glides across the copper sky, the clouds swirl in broad painterly strokes, and the surface steams in the warmth of a young sun. All of it is the quiet promise of what's to come. The air is still thick with volcanic breath, but something is changing in the way the light moves through it. The haze, once an unbroken blanket, now shifts and parts, letting shafts of pale sunlight spill through in trembling golden beams. These moments of clarity are brief, but they matter because each ray carries energy, and energy is the currency of transformation. Down in the warm, shallow pools, the water is busy with invisible work. Minerals leach from surrounding rocks, dissolving like sugar in tea. The heat from below stirs the liquid, ensuring that no molecule stays still for long. Carbon dioxide from the air joins the mix, slipping into the water, like a guest at a crowded party where it meets hydrogen, nitrogen, and other wanderers. Together, they form a bustling marketplace of elements, trading and rearranging themselves into ever more complex shapes. You might find yourself wondering, what would it feel like to stand here? would the ground tremble faintly beneath your feet as magma shifted deep below? Would the air be heavy on your skin, almost like wading through warm mist? Perhaps you'd hear the distant sigh of a vent opening, releasing a plume of gas that curls lazily upward. The moon continues its patient orbit, its pull ensuring the tides in these newborn seas never settle entirely. Water moves, crashes, retreats, and returns. With each cycle, it scrapes at the rock, loosening tiny fragments, carrying them to new places. This is erosion's first whisper, soft now, but destined to carve valleys and canyons with the patience of eternity. Occasionally, a wayward meteor still finds its way here, though nothing like the great bombardments of the past. These newcomers are mostly small, no more than the size of a car or a house, but they still make their mark. Each one delivers a cargo of minerals, metals, and sometimes complex organic molecules that formed far from here. It is as if the universe hasn't stopped sending care packages, small but precious, each one nudging the planet toward greater richness. Beneath the surface of the pools, there's a hum of potential. Molecules join, split, and join again, creating chains and rings that have never existed before. The heat, the minerals, the sunlight, and the movement of water work together like an orchestra, guided by no composer, but producing a melody nonetheless. And though there is still no life, the ingredients are now in the same room, the lights are on, and the music is playing. The rest will be a matter of chance and time. From above, this young world looks calmer, but not still. Clouds form and break, seas glisten, and the moon paints slow-moving shadows across the surface. Every part of it is in motion, not in the frantic bursts of its violent youth, but in the measured rhythm of a planet settling into itself. And somewhere in that rhythm, the story is shifting from the making of a world to the making of something that can call it home. The seas are deeper now, their surfaces rippling under a gentler sun. The haze that once cloaked the sky has thinned to a soft veil, letting through more daylight still filtered. Still pale, but enough to give the water a shifting silver-blue glow. You can almost feel the warmth on your eyelids as you imagine drifting here, a speck in the cradle of a growing world. Beneath those waves, something remarkable is happening. Tiny mineral surfaces, iron-rich clays, glittering pyrite crystals are acting like patient hosts at a long, slow banquet. They catch and hold onto small molecules, coaxing them into more complex forms. It's a delicate courtship. Two molecules might meet here, rest together for a heartbeat of geological time, and then part ways unless by some happy chance they bind. You might wonder if you could shrink yourself down to the size of these molecules. Would it feel crowded in this microscopic marketplace? Would you drift past shimmering mineral walls, bumping into clusters of carbon, hydrogen, oxygen, and nitrogen? Would you sense that something important was taking shape, even if you couldn't name it yet? Occasional sparks, microscopic lightning strikes within the water. Bursts of ultraviolet light slipping past the clouds add a dash of energy to the mix. Think of them as tiny chefs, stirring the pot, testing new combinations. The chemistry here is messy, full of false starts, but in the quiet chaos, the improbable sometimes wins. Meanwhile, the land is shifting under tectonic restlessness. Continents are not yet continents, but broad, dark rafts of crust that drift, slowly collide, and pull apart. These movements open deep cracks where seawater plunges down, meets magma, and returns in bubbling fountains, rich with metals and heat. The underwater landscape becomes a patchwork of vents and ridges, each one a miniature factory of chemistry. Meteorites still arrive now and then, but they are more like whispers than shouts. Small stones carrying hints of ammonia, methanol, and other strange gifts from the cold depths of space. It is almost as if the universe is unwilling to leave this planet entirely to its own devices, dropping in now and then to make a subtle suggestion. The moon's pull continues to choreograph the tides, and those tides sweep molecules from shallow shores to deep trenches, from one chemical neighborhood to another. It's a planetary mixing bowl, ensuring no single experiment happens in isolation. And though no eyes exist to see it yet, the stage is being set. The water holds not just dissolved minerals, but the seeds of something more, fragments of potential life, small enough to be invisible, but large enough to change everything. If you lean into the silence, you can almost hear the planet breathing a slow, even rhythm of waves, tides, and molten heartbeats deep below. This is not the frantic hammering of its youth, but the steady pulse of a world that is in its own way thinking ahead. The air above the young oceans feels different now, lighter, more complex. Volcanic plumes still rise in slow-motion spirals, but the choking clouds of the earliest days have given way to a gentler haze. In their place, faint streaks of blue hint at a sky beginning to show its true color, though still wrapped in the planet's protective warmth. Down in the shallows, chemistry is playing a longer, more deliberate game. Molecules that once danced in random chaos are beginning to form small, repeating patterns. Some link together into spirals and loops, fragile yet stubborn enough to survive a few extra moments before the waves pull them apart. These patterns are the first whisperings of information sequences that can, in a primitive way, remember. Imagine these early spirals as tiny storytellers, each one keeping a short, simple memory of its own shape. If you could pick one up carefully, like lifting a soap bubble, you might wonder, does it know it is part of something larger? Or is it simply content to repeat its form over and over in the quiet surf? Around hydrothermal vents, black mineral chimneys rise like underwater cathedrals. Their porous walls are riddled with microscopic chambers, each one a snug, protected room where reactions can happen in peace. Inside these spaces, heat and chemistry conspire to knit together more complex molecules, sometimes helped along by the steady drip of metal ions. These vents are like cosmic kitchens, each one following its own recipe, adjusting the ingredients according to the planet's shifting rhythms. Above the waterline, primitive islands of cooled basalt grow slowly from volcanic eruptions. Rain falls on them in soft sheets, collecting in warm pools. In these puddles, sunlight has more freedom to play, adding its energy to the mixture. Molecules here are stirred not only by heat and light, but by the simple act of drying and refilling condensation, concentrating them rainwater, diluting them again. From time to time, a fragment of space dust still arrives, fine as powdered sugar, drifting through the upper atmosphere before settling into the oceans. Each speck carries something new, a rare element, an unfamiliar molecule, or just the nudge of possibility. You might think of them as polite visitors, arriving without fanfare, staying just long enough to leave a gift. The tides, still guided by the moon's steady hand, continue their daily sweeping and endless shuttling of chemical ingredients between shore and deep water, between vent and current, between the known and the newly possible. Each cycle increases the odds that some lucky combination will endure, multiply, and eventually change the planet forever. If you close your eyes, you might hear this moment as a kind of gentle hum, the sound of a world quietly rehearsing the steps that will lead to life. It's not a sound carried on the air, but a rhythm in the water, in the stone, and in the soft glimmer of molecules finding one another against the odds. You drift now into an age of quiet persistence. The planet is no longer the furious newborn it once was. Its heartbeat has slowed, its temper softened. Yet beneath the calm surface, an invisible drama plays out in countless tiny corners. In the warm pools that gather on volcanic rock, the water is rich with the planet's own dissolved minerals. Here, early molecular chains, those shy storytellers from before, are beginning to grow bolder. They fold and twist in ways that shield their fragile shapes from breaking apart. Imagine each one as a little origami figure, tucking in edges to weather the waves. In some places, oily films spread across the surface of the pools, shimmering in sunlight. These films act like fences, keeping certain molecules close together, giving them the chance to interact more often. Within these soft enclosures, new chemical experiments unfold, molecules meeting again and again, until one combination proves unexpectedly durable. You might ask yourself, could these tiny fenced-in gatherings be rehearsals for the first true cell walls? Below the surface, near the ocean vents, something equally intriguing stirs. Certain mineral surfaces act as gentle hosts, holding on to molecules just long enough for them to link up in longer chains. These surfaces seem almost deliberate, like matchmakers pairing one molecule with another until a bond forms. The vents exhale a constant warmth, the kind you feel when leaning too close to a sunlit rock, and in that steady comfort, more complex reactions take root. Space dust still arrives, though more rarely, now adding exotic trace metals and rare isotopes into the mix. These gifts mingle with what's already here, sometimes sparking unusual chemical arrangements that might not otherwise occur on this world. A single dust grain invisible to the naked eye can carry an atom or molecule that tips the balance towards something entirely new. Storms sweep across the oceans, stirring up deep layers and scattering these chemical seeds across vast distances. Rain falls into every pool, every inlet, every rock crevice that can hold water. And the tides, those tireless custodians, continue to move everything along, blending the contributions of vents, sunlight, rain, and cosmic dust into one shared planetary experiment. It's a patient process, almost unbearably so, and yet the planet does not hurry. It seems to know that the best things are built grain by grain, cycle by cycle, until one day they are simply there. And here, in this still young world, something is drawing closer, something that will not just persist, but change, adapt, and perhaps even look back at the stars from which it came. You can almost feel the pause, the deep inhale of a planet, just before something irreversible happens. The seas are no longer empty wanderers of waves and light. They have become libraries of possibility. Every molecule drifting here carries a history written in both starlight and stone. In one sheltered bay, a cluster of molecules has found a way to enclose itself in a delicate bubble of lipids. It's nothing more than a tiny sphere, smaller than a mote of dust, but inside, it holds a private world. The bubble walls keep its contents together, just long enough for certain reactions to repeat, to refine, to build upon themselves. You might wonder, does it know it's different? Of course not. And yet this tiny bubble behaves like something that is trying, in its own quiet way, to continue. Nearby, another such bubble forms, then another. Most vanish quickly, broken apart by waves or changes in temperature. But a few survive a little longer than the rest. And with each survival, the odds shift tiny percentages, tilting in favor of greater complexity. The planet's chemistry is no longer just a chaotic dance. It is starting to resemble a waltz, with a pattern, a rhythm, a faint memory of direction. Space dust still visits, not in the fierce torrents of earlier days, but as rare glittering specks that fall like whispered reminders from the dark. They bring tiny packets of carbon compounds, amino acids, and even the occasional sugar molecule treasures that slot neatly into the planet's growing puzzle. Without them, the picture might take longer to appear. With them, certain steps come just a little easier. Volcanoes murmur beneath the seas, their plumes rich in iron and nickel. These metals help reactions happen faster, like quiet catalysts whispering, "Go on, try again," to the fragile molecules within those bubbles. Over countless cycles, one of these bubbles might stumble into a way of copying itself. Not perfectly, never perfectly, but just enough that its likeness lingers after it is gone. And in that imperfection there is room for change, and in change there is room for evolution. The tides go on, the rain falls, the world turns patient and unblinking. And one day, though, no one is there to see it. The first tiny spark of life appears, born of dust from distant stars, minerals from deep within the earth, and the endless, gentle urging of time. And now, as you lie there listening to the slow drift of this story, you can let your mind soften into that same patience. Imagine the earth young and quiet under a canopy of unfamiliar stars. No rush, no deadlines, no pressure, only the slow, certain weaving of time. Picture the oceans breathing in and out against the shore, the moon's pull steady and eternal. Feel how the air might have tasted, then rich, warm, faintly metallic, and how the light would shimmer differently without the modern sky you know. Let your breathing follow that tide, slow in, slow out, as if you too were part of this patient planet, as if your thoughts could settle into the silt at the bottom of those ancient seas. The space dust falls rarely now, like the faintest sprinkle of snow, each grain disappearing into the deep with no sound at all. There is no hurry here. There never was. Somewhere far above the stars that once sent those grains still burn. Their light takes centuries to arrive, yet it does arrive always without fail. The same quiet certainty that shaped the first molecules still flows through everything that has followed, through mountains, rivers, forests, and through you listening now in the stillness. If you've enjoyed this journey, I'd be quietly grateful if you'd give this video a like or tap that subscribe button for more peaceful explorations with the Sleepy Scientist. It helps more than you might imagine. And before you drift off, I'd still love to know, where in the world are you listening? From what time it is there? Leave a comment if you're feeling cozy enough to share. It's always a quiet joy to see this sleepy little community ripple across time zones and continents. Good night, sweet dreams.